So in this presentation, we talk about their way to accelerate MySQL with Apache Ignite. And really what we are going to talk about the sort of problems with MySQL, right? There are certain things in MySQL may not work very well. Some existing solutions which we have, and as well as Denis. Do you go by Denis or by Denis? Denis. Denis from Venice, right? Yes, that's right. So he will talk us about the power of Apache Ignite. So one thing I deeply believe is that when it comes to technology, there is no really silver bullet, right? You pretty much can't have it all, because all the decisions you are taking are going to pretty much have their own benefits and drawbacks, right? You have to be making trade-offs, right? For example, you guys hear a lot of talks on this conference about the new storage engine MyRocks with those fancy LSM trees, which has a great benefits for certain workloads, but for others, B-trees works much better, right? And you can't really have it all. Now, if you look, what is also interesting is, especially among their open source environments, we see a lot of the large-scale applications tend to use more than one technology in the data layer, right? So it's not just MySQL or Postgres or whatever relational database you would use. It's often there are multiple components which are used for their respected strong sides. And I think that works especially well with open source, right? Why? Because in open source, when you are bringing on additional technologies, it doesn't really come to you with hefty license fees, right? And in open source, you can go ahead and start using something, and at least it doesn't cost you anything to prototype and test things out, right? And this is not just about the license fees. Of course, if you go to Oracle and say, hey guys, I just want to, let's say, try out your Oracle NoSQL database, right, or whatever other components you may explore, you probably will get the evaluation version, and then the sales guys will nag you to death, right, during that evaluation process. Now, developers don't like that. Well, at least most of them don't, right? In the open source, what we can do is just to download any software without telling anybody about that, right? And only if you actually like it, then we can start having the conversation about getting commercial license, right, for many like open core products, or getting commercial services and so on and so forth, which I think is wonderful. I also think that the open source community is very good of building bridges and integration. One thing you may heard in the keynote today, right, is many of those guys which kind of brought on the time series panel, which you brought together from what you can see as like competing technologies. We're all talking, wow, you know, we actually can get the data from Prometheus, right? And we can expose the data from to Grafana, right? Or, hey, we actually integrate our technology to talk with Graffiti protocol, right? A lot of those kind of integrations, which are very good in open source technologies, because teams tend to work together on kind of a shared good. Now, having said all of that, I think balance is needed and important. Because if you use too many technologies, it can introduce complexity. And especially in a serious environment, every technology has to be supported, maintained, and so on and so forth. And I have like a little story here about this specific topic. I remember coming to one customer, and you know, that was a time when Cassandra was all the rage, right? And he was saying, oh, you know what? MySQL is kind of not optimized thing for, you know, data inserts. Cassandra with all kind of, you know, right optimized data structure. I want to store my logs in Cassandra. Well, that's probably true. I would ask him, how many logs do you have, right? Thinking maybe they have like billions of log records a day. Well, we have maybe 10,000 lines a day. Well, I would tell him at that point in time, it doesn't really matter, right? You can probably use SQLite just as well, right, to stack those those logs into. Well, anyway, I left them, as it happens with consulting engagement, came back a follow-up visit half a year later, and then we started to talk about, well, can we take a look at your log files? And I tell you, you know what, we kind of have a problem. You remember we spoke to you about this Cassandra project? We actually did implement, and now all of our logs are stored in Cassandra. Unfortunately, the guy who knew Cassandra left, and now we don't really know how to get him out of Cassandra anymore, right? Which was kind of, you know, kind of a funny story for me, right? In terms of really thinking how you can use those technologies well. You have to ensure that there are people who know how to use it. Okay. Anyway, so MySQL is really no exception here, right? MySQL is great in many things, but it is not great for everything. And I think the MySQL community has been pretty open in recognizing those limitations. And over time, some of them has been improving for years. Some of them are still pretty bad. So let me talk about some of those use cases which I list here. And I'll talk what is the problem and why MySQL may not always be a good fit for that. Well, hot data, and I would say as an example of that hot data could be something like a cache when you have a very heavy data modified, for example, maintaining some counters and so on and so forth, right, to simply heavy reads. When you get a large volume of simple requests, then MySQL may not be the most optimal. Well, because of high overhead due to SQL processing, parsing, and so on and so forth, right? For extremely fast queries, that actually can be significant. But also, MySQL really does not have very good memory-focused engine. Right? If you look at this case, InnoDB is general purpose storage engine, and it is actually pretty good, but it is not storage engine which is optimized for in-memory store. A lot of in-memory based engine, if you look at solutions like Redis, right, or Tarantul, MemSQL, right, wherever Memcache, they can do that a lot faster due to a lot of various design decisions. Also, MySQL has not been generally designed for high concurrency. It got better, and now you can have, let's say, thousands of MySQL users accessing MySQL at the same time. But if you really try to MySQL to drive many thousand transactions at the same time at single instance, it's maybe possible, but that would not be as efficient as in some other systems, right? So what our traditional solutions has been for those use cases? In case of MySQL, you can do certain things, like you can use a Memcache-D interface and protocol to alleviate some of the SQL parsing overhead. You can use a thread pool to deal with a large number of connections, right? But really what you also see a lot of use of external supplemental systems for here, such as Memcache or Redis. Anybody uses those? Or anybody has used those? Well, of course, right? So those are used to reduce the load of MySQL, which is often sourced as a sort of source of truth, right, and a main database of record. And we kind of want to be gentle to that and shave off some load when possible. Now, highly volatile data. Like if you're thinking about a lot of updates, especially to updates to a single row, that is not very efficient in MySQL. It is not bad, but if you really look at a very high number of updates, it's not very efficient. You would be, I think we actually had a presentation on this conference with Alibaba folks talking about how they had to implement some MySQL extension to deal with the hot rows, because otherwise we couldn't sell some of the stuff fast enough in China, right? Well, I mean, you know, everything is big in China, right? So, and the reason for that is because SQL database as MySQL is driven by around full transactional ACID semantics. And that requires a lot in terms of transaction isolation, so on and so forth, and SQL semantics and query, which is, has quite a lot of overhead. It also has disk-based durability and the pessimistic locking which comes to that, which all can impact that. Now, if you look in this case in terms of solutions, we also can do certain things on the MySQL level, like we can do data design to alleviate some of those problems. For example, very commonly, if I have to count a row of many updates, I may create several rows, right? Then I would modify one of, let's say, 10 or one of 100 random rows, right? So there is not as much contention, right? We can, of course, make sure we optimize MySQL well. We can use parallel replication, right? Which was often a problem for very hot data in MySQL. But we can well update that on master, but it cannot make it to a slave due to replication bottleneck, right? That's often was a problem. And again, we use often very similar external systems, right? Memcache and Redis to deal with those hot data, volatile data, do a lot of updates, and then sort of dump that to MySQL every so often. The next one is large data volume. MySQL is designed as a single node system, right? And this is because MySQL was designed more than 25 years ago, right? So, and while MySQL was kind of adjusting for this new modern distributed cloud environment, hasn't been built for that from the ground up. So because it's designed first and foremost for a single node, it's limited in amount of CPU, amount of memory, and other resources it can use. And while MySQL supports sharding, the manual sharding solutions are painful, right? Did anybody here experience painful sharding MySQL? No one? Oh, I see some hands, right? And I guess the rest of you didn't have to do MySQL sharding. What's that? Decided not, right? Yeah. So sharding is a pain in MySQL. That's unfortunate reality for that. And that's especially true with some complicated queries. For sharding, cross-shard queries are painful. But even if you have another issues is where, dealing with analytics, right? MySQL is single-thread operation that's not great. Now, in this case, we again have some solution. We have manual sharding solutions like VTest or Proxy SQL, which can support sharding, as well as there are many external solutions, right? Now, there are solutions where if you're building on, for example, Redis or Memcache, there are sharding solutions for that. People are also often using some solutions like MongoDB or Cassandra, right, because they make sharding less painful. We also see the guys like Clusterix, right, for example. You can meet them at the Expo Hall. They have the MySQL comparable kind of sharded engine, right, or ScaleArc, right, which have something similar to Proxy SQL, which also supports sharding. So, number of solutions out there. MySQL doesn't have a perfect bullet. And the next one is analytics. The challenge in MySQL is that MySQL does not have any column storage as a problem. MySQL optimizer is quite limited in techniques. It can really apply to very complicated queries, right? So if you have like joining 25 tables with a lot of subqueries, MySQL optimizer is not really designed to deal with those queries well. It doesn't have any parallel query execution to use multi-cores even in a single query, a single system, not even to talk about their distributed processing on multiple nodes. So what do we do here? Well, in MySQL, we can try to do configuration, we have more hardware, try to do kind of a schema design to work it around, avoid those kind of queries which crunch a lot of data. But frankly, it is limited. And I remember like 10 years plus ago, we often would kind of try to do something stupid with MySQL, like, oh, you know what, we can't run those queries separately, let's run some Perl scripts, right, then, which would kind of run parallel queries on multiple slaves and aggregate results. And this is all before kind of Hadoop was invented, right? Now, what we see with MySQL now is there are a number of external solutions which exist. It could be Hadoop and Spark. That ecosystem is very strong for data analytics. If you're looking for something more kind of SQL driven, there are solutions like Vertica, like ClickHouse, right, which is also open source engine which presents here at the expo floor, as well as solutions as MariaDB column store, right, which even though it kind of has MariaDB in its name, is really entirely different data store and an execution engine. Then full text search. Now, full text search exists in MySQL, and now it's even supported for InnoDB tables. But I believe that if you have a data size which is somewhere larger than your home DVD collection, right, if you still have any, then MySQL full text search doesn't really scale very well for those sizes. And again, because there is no parallel processing, but also because MySQL wasn't really designed first and foremost with search in mind. There is no thinking about relevance options or natural language processing, figuring out, you know, the meaning, right, and sentence structure. Nothing of that exists, right? There is not a lot of support for facet search. There is kind of GIS supporting searches, but that's pretty inefficient. All of those are MySQL limitations. And frankly, if you look at, I don't know any kind of large-scale system which really would rely on MySQL full text search for operation, right? What do we use? Well, again, small-scale search for some simple applications, right? Maybe up to a few gigabytes of data size, works pretty well in MySQL those days. But now we can see a lot of folks using external solutions in this case. Elastic, right? Again, the guys spoke to, they have a very common choice, right? Or some people use Solar, maybe even Lucene, kind of an underlying technology for those things. Sphinx is another open source full text search system which people use, right? So there are a lot of those systems which are commonly used to supplement MySQL with what MySQL doesn't do well. Okay, now, I mean, what I think is interesting in this case is to see what is in our ecosystem, which often have to kind of gravitate to all the systems, all the technologies which we already know about. But there are, in open source ecosystem, the new solutions constantly appear. And I think that is very exciting to see what else exists out there. And I believe Apache Ignite, that is one of a new projects, which is relatively new, right, compared to Memcache and Redis, who has like long history. And that is what Denis is going to talk to you about, you know, how wonderful Apache Ignite is. And what can I do for you?
Yeah, hello everyone. Thanks, Peter, for excellent beginning of our talk. And today, for you as MySQL users, developers, and for those who use MySQL, I believe, in production, I want to suggest one of the solutions you might want to keep in mind if you want to resolve some of the issues that were described by Peter throughout these 20 minutes. So first of all, I will explain you and explain how actually you can resolve sharding issue with MySQL. Because Apache Ignite is a platform that basically built on top of a cluster of machines, which automatically gives you so-called partitioning or sharding capabilities out of the box. Yes, we don't. Our product doesn't. Provide any feature that is integrated with MySQL to enable sharding, but combining both MySQL and Apache Ignite, you can get advanced performance improvements because the data sets will be located in memory in a distributed way, close to your CPUs. And at the same time, the data sets will be persisted on disk in MySQL. For the case if you, for instance, need to restart a cluster of your machines and you don't want to lose your data. Okay, so as for me, a couple of words. My name is Denis Magda, and presently I take a role of a product manager at GridGain Systems. And at the same time, I'm Apache Ignite PMC chairman. So at the same time, I joined GridGain and I became a part of Apache Ignite community almost 2 years ago. I'm still, despite of the fact that presently I take a management role, I'm still one of the most active contributors to Apache Ignite. And I joined GridGain as a software engineer. Then I spent almost a year helping GridGain and Apache Ignite customers deploying that products in production. And this is why you can expect to get from me all the technical details you want to know. But this presentation will be sort of a brief overview so that you can form an understanding on what Apache Ignite is actually, what Apache Ignite is. So the agenda is just quite straightforward. I will just show what do we mean under the Apache Ignite in-memory data fabric and why we call precisely it this way and not the other. And next, I will just give you an overview of the most frequently used components we have in our product. And such of the components is, the first one is clustering, then computations, then data grid, which is basically a foundation for your for our distributed data storage. And on top of these components, you can execute distributed SQL queries. You can implement microservices-based architectures, and so on and so forth. But for you, as for MySQL users, I think that the most important bullets would be in-memory SQL grid, data grid, and clustering. So in-memory data fabric. So Apache Ignite is not just a computational engine. It's not just a distributed storage. It's more than that. So in reality, it's a combination of multiple building blocks, of multiple components that were engineered together in order to give you one of the best performance that you can get from in-memory computing technologies. And at the same time, having this exceptional performance, you can rely on the fact that all the computations, all the data, and all the components are built in a sense that we do care about fault tolerance, we do care about high availability, and on all other characteristics that are extremely important for distributed systems. If you take a look at this slide, you will see in the middle Apache Ignite in-memory data fabric. So here is, you can just plug it in. You can slide it in between your applications, probably some of the existing applications, and your persistent storage like MySQL. On this picture, in the middle, you can see orange blocks. These are your cluster machines. And actually, all your cluster machines have to interconnect with each other. And once this happens, you can start working with your cluster. You can start harnessing it. For instance, the first thing you would like to do, you might want to do, is to put data there. And you will be putting it just, using basic key value APIs, because at the implementation level, our data grid is a distributed key value storage. And then when you will be flushing data into the cluster, the data will be spread out across all your cluster machines available uniformly. After that, once you have your data in the cluster, you need to interact with it. You need to talk to your data. You need to get some benefit from this. And here is, on top of that, you can use a variety of different APIs, like distributed SQL engine. So you can execute distributed SQL queries, which are NC99 compliant. So we do support all sorts of aggregations, distributed joins, and so on and so forth. Everything that is needed that is widely used in, I think that in almost all production environments. Then, if you want to go forward, if you need, let's say, some distributed computations that need to do some advanced calculations, then here is, you can rely on Compute Grid, which is our fork join or MapReduce framework built specifically for Apache Ignite Memory Data Fabric, and so on and so forth. As for the persistence, so when I'm trying to recall how many Apache Ignite users or customers went in production without heavy persistence, I would just I would just recall only 2 or up to 5 of them. Most of the people still go in production with some persistence enabled. And as for the persistence can be easily integrated with Apache Ignite. You just need to provide an implementation of a so-called cache store interface. And once this is done, all the data that goes into the cluster will be automatically pushed into your persistent storage. Your persistent storage can be integrated in write-through and read-through modes, meaning that, for instance, if you try to get some data from your cluster and a key or a set of the keys are missing in memory, then the data fabric will go to your data storage, like MySQL database, and will retrieve the missing keys and values from there. And before we look into those components, I want just try to explain why in memory. And why such products as Apache Ignite are becoming extremely popular and useful nowadays. So if you take a look at this chart, this chart represents the price for different storage disks or RAM or flash-based storages and so on and so forth per different years. And here, as you can see, that we are interested in this green one, which is for RAM, for volatile memory. And if you pay attention, you will see that throughout all these years, the price for these chips for RAM is going down. It's being reduced significantly. And this is why in 2010s and now these years, a lot of customers look, with a sort of appreciation to in-memory computing engines, because now RAM is not as expensive as it was before, and now you can build a cluster of hundreds, terabytes, or even petabytes of data that will be stored in memory, in RAM, and it will not cost you more than buying, a powerful, kind of expensive machine, let's say from Oracle or from other hardware vendor. And at the same time, a lot of in-memory computing products, a lot of like Apache Ignite and Memory Data Fabric, from the very beginning, they are built as a distributed systems. As distributed systems, from the beginning, we cared about data locality. So that was our one of the main goals, to make sure that the data is spread out uniformly across your cluster nodes. That if you execute distributed transactions, that all the transactions will comply with a seed semantics. If you want to execute SQL queries, then every SQL query will return a complete result set without any exception, even if your cluster nodes goes down throughout the time a query is being executed. And how do we do this? So actually, everything is based on I just listed several components, but the two first components that Apache Ignite's Holy Grail is advanced clustering. So before you can start work with Apache Ignite, you just essentially need to create your cluster of machines. And this is one of the things that is probably the simplest one. What you just need to do is to allocate some resources. You can buy virtual machines from, or you can just host virtual machines on different cloud systems like AWS or Google Compute Engine, or you can purchase your own hardware and set it up in your data center, and that's all. And after that, what you need to do is to create a configuration, setting, for instance, IP addresses of all of the nodes that might be in your cluster. And once once you will be launching your nodes, they will automatically auto-discover each other, and they will form a single cluster of all of the machines. There are other approaches like if you don't want to predefine all the IP addresses you have, and sometimes it's not possible, you can use a variety of other implementations of so-called IP finders that allows cluster nodes to auto-discover each other in a distributed systems, like for AWS, for Kubernetes, and for other systems we develop special IP finders so that once you start an Apache Ignite node process, the node will be able somehow automatically discover the rest of the cluster. Then, once your cluster is up and running, once you have all your cluster nodes, you can start leveraging from this. And the first thing that can pop up in our mind is the utilization of a memory compute grid component. So as I said, it's our MapReduce fork join framework developed specifically for Apache Ignite, so you can't use it separately. So all the components that I'm presenting today, they're designed for Apache and can be used only as a part of a single platform. And if you take a look at this picture, basically the concept is similar to other distributed computational frameworks like Spark, for instance. You just have some task or a set of the task, and you want to get everything from all the resources you have. And then you just feed this task into the cluster. And then depending on your computational logic, the task can be executed on all the machines you have or on a subset of the machines that store a specific subset of the data. Also worth to mention that if a task fails, if one of the small pieces of the task fails throughout the execution, it can be automatically rescheduled for the execution, so depending on your preferences. Then, as for the load balancing suggests that if a task can be potentially executed on multiple nodes, then compute grid will identify, for instance, current load of every possible candidate and will make sure that the task is executed on underload machines rather than on the overloaded machines. But one of the things about compute grid that I personally like most is its so-called affinity collocation of data with computation. So affinity collocation suggests that in this scenario, is that if you have some computation and you want to execute it close to some data that is located in your cluster, then you don't need to grab this data from your cluster machines, bring it to your application, update it there, and send it back, because you will overutilize your networking resources. But rather, you can develop your computation, send it to your server machines that store specific data sets, do the calculation, and that's it. For instance, I have one of the production use cases that I usually boast about when we're talking about compute grid. One of GridGain customers, it's a huge financial institution. It's a bank, the bank called Sberbank. It's one of the largest banks in Russia and Eastern Europe. They have, as many other banks worldwide, they have to do one regular task at least once a month. So they have to iterate over all the savings accounts they have, and they have to apply some interest. And so before they switched to GridGain, the workflow for this operation was pretty standard. So late night, when the whole country just sleeps, they were going to huge Oracle database, a single machine that ran the whole Oracle database. They grabbed all the data from there, updated it, and sent it back. And this whole operation took them 2 hours and 30 minutes. When they switched to the GridGain, they just implemented this update logic using Compute Grid, and then they decided with Compute Grid they will no longer need to get data from there. They sent those computations to the server nodes that were in the cluster, and the same operation were completed in 10 minutes. And this was done without any optimization on Apache Ignite or GridGain side. That was done just as a part of POC. And this is just for you to have an understanding on what would be a difference if you decide to send a computation and execute your computation close to the data, rather than picking all the data and bringing it to your application and send it back later on. Data grid. So actually, I think that there is no in my experience, so every customer of Apache Ignite and GridGain that goes in production, they use data grid because they need to have data in the cluster. And data grid is our distributed key value storage, just the same storage as of, I don't know, as Redis, as Hazelcast, as other data grid vendors. But it's not a kind of, it's a unique storage, because at the implementation level, it's still a data grid. You can talk to it using standard key value operations like get a key, put a key, or get a list of the keys. But this storage is complies ACID semantics. So simply we implemented two-phase commit protocol, and which means that if you start to execute distributed transactions and you try to update data that is stored on different nodes in different data sets, then our platform guarantees that either the whole transaction will be committed successfully cluster-wide, or it will be rejected and will be rolled back. And at the same time, like it's shown on this picture, if you have a database or like other storage, like MySQL, integrated with your cluster that is in memory, then all these ACID guarantees are true for all the data that is in memory and that is on disk, let's say, in MySQL. So our transactional protocol can find out that there is a kind of relational database and that is used as a storage, and it will make sure that the whole transaction, if the whole transaction is committed, it will be committed, let's say, in MySQL and in memory cluster-wide. As for the storage, so the product Apache Ignite is a Java application. So it also can suffer from garbage collection policies, depending on your application code. But as a platform, we do support so-called heap memory. So it's a manageable memory region that is not visible and it's not accessible by Java garbage collectors. And usually nowadays, all of the customers, they store the data sets in a heap region, just in order to tolerate garbage collection policies. And even more, in the next version of Apache Ignite, which will be released in a couple of weeks, we even improved, we re-engineered our previous of heap storage. Now we call it page memory. It can remind you a memory architecture of a Unix system like Linux. So where we split all the memory on pages of different size, which allows us not only tolerate garbage collection policies, but also avoid memory fragmentation. for you as for MySQL users, I think that it will be beneficial to know about our in-memory SQL grid capabilities. So this is the API. This is NC99 compliant distributed API that is built on top of Apache Ignite in-memory data fabric. And it allows you basically execute all well-known queries that are defined and specified in NC99. So for instance, all sorts of aggregations, cross-cache joins, distributed joins, all this is supported out of the box. At the same time, if you prefer to update your data sets using DML statements like insert, update, or delete, you can do this. So as I said, so the data sets can be updated using basic key value operations, but at the same time, you're free to use inserts, updates, and deletes if you like this. And even more, for Apache Ignite, sure, we do support Java API, so Java library, which is the first that gets the first the latest features that we release. But at the same time, we do have libraries for C++ and .NET, and even more if you don't want to use, some special library developed, but your case is just, to execute SQL queries, then take a look at our JDBC or DBC drivers. So for instance, if you have PHP or Python application that interacts with your MySQL database, and you just want to accelerate your MySQL database by plugging in memory data fabric on top of your storage, then you still can keep using JDBC or DBC. And most likely, you don't need to rewrite your code at all, because you just need to provide a configuration, and that's it. And you are free to connect to a cluster from the driver side and work with your data sets this way. And finally, just to emphasize on this one more time, SQL Grid, as many other components, are built with was built with high availability and fault tolerance guarantees. So as for the other components like in-memory service grid, I will just list them briefly. This is just an API that can give you a way to deploy your services cluster-wide, and the cluster will take care of all the life cycle of fault tolerance and of load balancing of your services. Usually, I do suggest to use this to use service grid for microservices-based architecture if you build one. Next, as for the streaming, so the streaming is needed when you want to, for instance, ingest a lot of the data into your data grid. Then, for instance, it can be used at the time you preload the data into the cluster, or at the same time, let's say, if you have some IoT solution like a mesh of different sensors deployed in some of the environments, you also can grab data from there and stream it in the real time into your cluster. And then also, while the data is being streamed, you can process it, performing some calculations. The other component that is that might be interesting for those who work with Hadoop, it's called Hadoop Accelerator. What it does, it consists of two things. The first one is Apache Ignite in-memory MapReduce. MapReduce implementation. So it just operates faster than the default one available for you in Hadoop. And the other is Ignite in-memory file system. So Ignite in-memory file system is HDFS compliant file system. And what you can do, you need to plug it in between your Hadoop-based application and your HDFS, and that's it. So usually it should take you, I don't know, from 10 minutes to a couple of hours, depending on your use case. And you don't need to write a single line of the code if you want to get performance acceleration. And the performance acceleration depends on your use case. But according to our observations, you can get up to 2x performance acceleration or even more. It depends. And finally, for Spark community, we developed so-called in-memory shared RDDs. It's just one more API on top of your cluster. So if you have your Spark application that heavily uses, let's say, RDDs, and for instance, you need to share the state of your RDDs among different Spark workers, or you want to execute SQL queries extremely faster, then you can use our in-memory shared RDDs. So in this in-memory shared RDDs, they fully comply to a Spark specification. So, and just once you have this RDD in your cluster, so your Spark-based application can leverage from this capability, so that all the application can share all the data sets stored in this RDD, and you can execute SQL queries, our Apache Ignite SQL queries that do support indexing. Because as far as I know, presently Spark still doesn't support indexing capabilities for its engine, which became a kind of a bottleneck for that application, for those applications that heavily rely on SQL capabilities. So that's all from my side. And today, if you want to learn more and you want to hear more about Apache Ignite SQL Grid, about our SQL capabilities, you can visit my 25-minute talk today in that room. And in addition to the theoretical part, I prepared a special demo that I would like to show to you. And throughout this demo, I will show how you can quickly create a cluster of machines that are connected with your MySQL database. And when we will be updating, let's say, data sets stored in your cluster, I will show and I will demonstrate that all the data sets will be updated both in memory and in your MySQL database. So thanks for your attention. And if you have I think if you have any questions, we still have some time.
Where you're going to slide it, between the application and the MySQL database. Is there a seamless mapping? How do you map it from, RDBMS schema to the value store? How is that? Is there a tool that does that for you? How does that happen?
So the question is, in short, the question is, if you are sliding in memory data fabric between your application and storages, how you make sure that the data is updated in memory and on disk, and how we just turn into key value updates into relational queries. So this is what Ignite has is just cache store interface, a special interface every storage has to update. It can be relational database, it can be Cassandra or MongoDB. And then when you, let's say, update a set of the keys, we just call this storage interface saying that, look, these keys were updated. And this implementation, like relational database implementation, it will just take these keys and prepare inserts or updates queries that will go to your database. And as for the schema, if you are migrating from your, or if you want just to leverage from both solutions, from, let's say, MySQL and from your in-memory layer, then when you will be migrating, you can automatically migrate the schema from your MySQL. And when you do this, you will get special cache configurations for your Apache Ignite cluster. And inside of this configuration, we will automatically define, all the indexes you have on disk and all other parameters.